Okay, so now we're moving on to the topic of analysis of variance for categories, or if you prefer, factors or groups. So the learning objective for this chapter is to understand how to model the effect of categorical variables on a continuous variable. So what if we have more than two populations? How can we test if they have the same population mean? If we only had two populations, then we've already looked at how to handle that using a t-test. But what if we have more than two populations and we want to understand whether they have the same population mean or different population means? So analysis of variance was originally introduced as a concept as a way to simultaneously test for any difference in a means of a set of populations, assuming that they have the same population variance. So there's no simple confidence interval idea anymore, but we can still do a significance test. So this time, the thing we use to test for the difference, in other words, our test statistic, needs to be a bit more complex. So the idea is as follows. If the populations do really have the same mean, then the sample means should be similar, and hence the sample mean should be close to the overall mean. So we can look at the ratio of the squared deviations of the sample means from the overall mean to the deviations of the individual data points from their respective sample means. So if the ratio is large, then we don't believe that the sample means are similar, and hence that the population means can be the same. So this should sound familiar because it's essentially the same idea we use for multiple regression. So for a one-way classification, meaning we just have one categorical variable, or one-way ANOVA, the table looks like this. So you can see here, in the same way, we've got between groups, within groups, and the total. So within groups corresponds to the residual in the multiple regression model. That's the variability that our model does not explain because it's variation within the groups. The between groups part is the same as the model part in the regression model. So we can calculate the total sum of squares. That's again just the variability around the overall mean. The sum of squares within is the variability of our individuals from the group means, and then the SSB, the sum of squares for between groups, is just the difference. And if we have k groups, then again obviously we'll have k minus 1 degrees of freedom for the between groups, and obviously again we start out with n minus k degrees of freedom because we've subtracted the overall mean. So the residual or within groups term has n minus k degrees of freedom. In the same way as in the regression models, we calculate the mean squares, which is we scale the sums of squares by their degrees of freedom. And then lastly, we look at the F ratio, which is comparing the mean square for between groups to the mean square within groups. So the precise formula are not too important, but the relative simplicity is attractive. And of course, we can extend this idea to much more complex situations, in particular where there's more than one grouping. So for example, if we have two classifications, then we would have factor 1, factor 2, the residual, and the total. So that makes it relatively easy to identify the different important causes or sources of variability. As I've said, if the sum of squares are if the groups are very different, the SSB will be large, and hence the MSB will be large if that difference is large relative to the number of groups. And again, if the variability left is small, then SSW will be small, and if it's small given the sample size, then MSW will be small. So overall, it's easy to see that large values of F indicate that there is good evidence that there are indeed group differences, so we can reject the null hypothesis of no group differences. So statistical software will tell us whether the F value is big enough to reject the null hypothesis. Usually it tells us the significance level at which we should reject the null. That's called the observed significance level. If there are only two groups, of course, we can still use the t-test, but the t-test is equivalent to the f-test. The F statistic is just the square of the t statistic. So again, it's just saying We don't really care what the direction is of the difference. We just care about how big the difference is. In that case, it's k equals 2, so we just have 1 degree of freedom in the numerator of the f statistic. So again, we sometimes use r squared as the summary of the usefulness of the grouping, where r squared will be the SSB over SST. In other words, it's the proportion of variability explained by the grouping. As I've said before, we put explained in quotes because we don't know necessarily that this is causal. It's just how much of the variability goes away once we take into account the group membership. So again, r squared is scale independent, so that allows easy comparisons. And again, there is a problem with r squared in that if we add an extra group, r squared will always go up. So as in the multiple regression case, we use the adjusted r squared to allow comparisons of groups of models with different numbers of groups, and we adjust the r squared in just the same way, where we divide SSW by n minus k instead of by n minus 1. So our general strategy is, of course, to find models that are simple, have a good explanation, and are easy to interpret. So simple means few terms. Good explanation means generally high r squared or high adjusted r squared, and easy to interpret in the sense of on a theoretical basis or a consistency of the variables. So, of course, we can use more sophisticated selection criteria than the ones we mentioned in the regression models, such as AIC and BIC. So I'm going to start by looking at a simple example of a randomized controlled trial. So just to remind you, randomized controlled trial means that the individuals should have been randomly allocated to the treatments. And in this particular case, we have 3 possible treatments. Treatment F is a placebo. So just to remind you, placebo means I do nothing. That means they were still given a tablet, but the tablet had no active ingredient, whereas the other 2 groups, D and F, are the 2 active drugs that we want to compare against the placebo. By using the placebo, that gives us an ability to take account of the fact that some people may be improving even without treatment, or indeed that some people may improve simply because they think they're being treated. So on the left-hand side, we have a graphical representation of our data. So in this situation, low values of y are good. So just by looking at the plot, it does appear that both drug A and D are better than the placebo. What we can't tell from that graph very well is whether that difference is significant. So let's have a look at the right-hand side. The right-hand side says our r squared is only about 22%. The adjusted r squared is only about 17%. The root mean square error, that means S, is about 6. And we have 30 observations. And then we have our analysis of variance table. We have 3 treatments, so that means we have 3 minus 1 is 2 degrees of freedom. We have 30 observations, so the degrees of freedom on the total is 29 and minus 1. The difference between those 2 is 27. So we can calculate the mean squares for both the drug differences, and for the error term, we can calculate the F ratio. The F ratio is not too small, it's nearly 4, but this is a relatively small sample. So the observed significance level for this overall F test is only about 3%. So we do have some evidence of a difference between the 3 treatments, but it's not a very strong piece of evidence. And again, remember, this is statistical significance. This has nothing to do with whether the difference is clinically important or clinically significant. So practical significance is a separate issue. Now, of course, quite often we want to compare the groups. So this is what we call multiple comparisons. So for example, we might want to compare pairs of groups to see if they're significantly different. So the simple approach is just to use a t-test for any pair of groups. But the problem is, like the one for multiple regression, there are many possible tests. Even in this case, we already have 3 possible pairwise tests. So one approach, of course, is that we only look at the pairs if the overall f-test is significant. That helps a little bit, but another better approach is to use a modification of the t-test that takes into account the multiple comparisons being done. So this was introduced by a very famous statistician called John Tukey. One of the things that's so wonderful about John Tukey is he understood the importance not only of having good ideas, but having a good presentation for your ideas. So John Tukey is famous not only to statisticians, he's also famous to computer scientists, who was one of the inventors of the fast Fourier transform. But in this particular case, what he said was, my approach is the honestly significant difference, or HSD, instead of the t-test. In other words, I'm honest in that I'm taking into account the fact that I'm doing multiple comparisons. I'm not hiding from you that I'm doing multiple comparisons. Now, this particular example is relatively simple because we only have 3 groups. But imagine we had 10 different groups, then there would be 10 times 9 over 2, which is 45 different comparisons. So this becomes a major issue if we have many groups in our comparison. So let's have a look at our drug example if we look at the Tukey-Kramer honestly significant difference. So what we're comparing here is both ways of looking at the data. So at the top, you've got a graphical representation. It's not too easy to see what's going on there, but if we look below, it gives us a nice summary. So you will see that on both the left and the right, of course, we can see the means for our 3 groups. So for the placebo, the mean is 12.3. For drug D, the mean is 6.1, and for drug A, the mean is 5.3. And this issue of connecting letters tells us whether groups are significantly different. Levels not connected by the same letter are significantly different. So this is telling us that if we just do the t-test on the left-hand side, then drug D and drug A are both different from the placebo, but they're not significantly different from each other. And if we look at the bottom part on the left, it's showing us the confidence limit for the difference. So the difference between D and A is 0.8. The standard error of that difference is 2.7. So the confidence interval goes all the way from minus 4.7 something up to plus 6.37. So you can see it's a very wide interval that clearly contains 0. If we look at the confidence interval for the difference between the placebo and A, it's saying the difference is 7 with a standard error of 2.7. So you can see the confidence limit goes from 1.4 all the way up to 12. Clearly does not include 0. So that's why we have an observed significance level of 1.6%. The difference between drug D and the placebo is 6.2 on average, standard error of 2.7. So the 95% confidence limit goes from plus 6 up to plus 11.8. So that again doesn't include 0, so the observed significance level is about 3%. So that looks like good news, but of course this is not taking into account the fact that we're doing 3 tests, not doing 1. So we look at the right-hand side where we've taken into account that we're doing multiple tests. You'll see first of all in the middle there, the connecting letters show that actually we can no longer distinguish between drug D and the placebo because they both have a letter A there, but we can still distinguish drug A from the placebo. So if we look at the differences, of course, the mean difference hasn't changed, the standard error hasn't changed, but the confidence intervals have changed. So you'll see the confidence interval for the difference between D and A obviously is still not significant. The difference between A and F is still significant because the confidence interval after adjustment now goes from 0.27 up to 13.7. Doesn't include 0, so we have an observed significance level of about 4%. But the difference between D and the placebo, the confidence interval now goes from minus 0.5 up to 12.9. So this is obviously not significant at 5%, and indeed the observed significance level is about 7.5%. So this is warning us that actually, if we take into account the multiple tests, yes, it does appear that at least drug A is better than the placebo, but it's not clear whether drug D is better than the placebo. Okay, so that's one way to look at our data, but there are other types of questions that we might ask. So a contrast, it says here the definition is a linear combination of group effects. So the simplest example would be these pair differences we've just looked at. But there are more sophisticated questions that we could ask. So if we can think about this situation here, I said that we had 2 drugs and a placebo. And I said that we weren't able to distinguish between the 2 drugs. They seem to have fairly similar effects. So we might ask a somewhat different question. So if you imagined you were trying to decide which drug to use, so in Hong Kong, as in other countries which have public hospitals, they often have some form of evaluation process to try and decide which drugs they should use in the healthcare system. And there are several different elements to go into that decision, including, of course, safety and cost. So we're not going to talk about those here, but there are also questions about how good is this drug? Can we be sure that this drug actually works? So in this situation here, we're trying to decide actually whether to use a drug or not is maybe the first level of question, and then the second level of question is which drug to use. So in that situation, if it turned out that drugs A and D actually had similar cost and similar safety concerns, we maybe don't really care too much whether to use drug A or drug D. We simply want to know whether the intervention of using any drug is better than the placebo. So in that situation, we're asking a somewhat different question. We essentially want to know whether the average effect of the drug is better than the placebo. So this might be our first question. Are we quite sure that it is worthwhile using one of these drugs? So what you've got below here on the page is a test whether the average effect of A and D is better than the placebo. And so of course this means we're comparing 2 groups of drugs, so there's 10 in each of those groups against the 10 in our placebo. So we're making use of more data in this test, so not surprisingly it's more sensitive. So in this case the F ratio is nearly 8 and the observed significance level is below 1%. In other words, it seems quite clear that there is a drug effect even if we're unclear based on this data as to which drug is better. So at least it's persuasive that the drug itself, that at least one of the drugs is useful, but we can't tell which one is the better one. Okay, so what if we have more than one classification? So if there's more than one classification, this can work in more than one way. We have what we call a nested or hierarchical classification or a crossed classification. So nested or hierarchical means that the second classification works inside or is nested in the first classification, whereas crossed means that both classifications are generally applicable. So imagine that we were looking at gender and marital status. Those would normally be crossed because those are separate issues. What's your gender and what's your marital status? Whereas imagine we were dealing with data from schools, from students, we would have perhaps school and class number. So your class number is usually a within school classification. It's nested inside your school. So that would be a nested or hierarchical classification, where sex and marital status would be a crossed classification. So let's look first at crossed classifications. So for two crossed classifications, this is what we call a two-way analysis of variance. We now actually in principle have four possible sources of variability. We have classification 1, we have classification 2, and we have this thing class 1 times class 2, or it's sometimes written as class 1 dot class 2. What is this? This is the interaction between class 1 and class 2. It means that the class 2 differences maybe are not the same for different values of class 1. So for example, if we were looking at gender and marital status, it might mean that the differences between single and married people are different for males and females. Right? If this is not the case, we would say that we might be able to just treat sex and marital status as separate classifications without the interaction effect, and just combine this interaction effect back into the residual. So the residual is the part that's left over. This is the variability within this two-way classification. So the residual would be variability within male single, within male married, within female single, and within female married. So that's within the two-way classification groups. That's the residual part. Okay, so for models of this sort, we usually check for lack of fit. So lack of fit means, of course, we hope to not reject this hypothesis. This sort of analysis is possible if we have what we call replicates. What are replicates? Replicates means that for some combinations of the factors, we have multiple data points giving us a way to estimate what we call the pure error. In other words, the differences between respondents with identical factor combinations. So this excludes any possibility that our model does not include the necessary interaction terms between the factors, because we may not be including all the interaction terms. So we can divide up the residual error into what we call pure error, and the other part is the lack of fit. So this checks whether our model looks okay in the sense of whether we have excluded interaction effects which we need to include or not. This is a separate issue as to whether there are missing factors, right? So if there are factors missing, this assessment of lack of fit won't help us. Lack of fit helps us identify whether there are missing interaction terms from our model. So when you're designing an experiment, replicates are obviously a very good idea, as they allow a diagnostic check that does not depend on whether the model is correct. So we're going to have a look at an example of a multiple way classification. We're going to look at a rather silly example of making popcorn and looking at which of three factors and their interactions predict what the yield is. So the yield is presumably how good we are at selling the popcorn or how happy people are with our product. Okay, so we're going to have a look at these results to try and understand what's going on in this case. So this particular case, we have these three factors. We have popcorn. We have two types of popcorn. We have gourmet and normal. We have two types of oil, two amounts of oil rather, little and large. We have two batch sizes, little and large. Okay, so if you think about it, that means there's 2 times 2 times 2 combinations, which is 8. If you look at what's written up at the top, we actually have 16 observation. So that means we have 2 replicates So that means we can actually test whether or not we have lack of fit. I'm not going to show that part here for simplicity. But if we put all of the terms into our model, so this presentation here is allowing for all the interactions. So we've not only got our three variables, popcorn, oil amount, and batch. We've got the three two-way interactions, popcorn against oil, popcorn against batch, and oil against batch. And we've also got the three-way interaction, popcorn, oil, and batch. So this is a designed experiment, so it's balanced. So we can divide all these parts up. If we look at the results here, you can see that the three-way interaction does not appear to be significant. And of the two-way interactions, the only one that seems to be significant is popcorn crossed with batch. And if you look at the main effects, you can see popcorn is significant, oil amount does not appear to be significant, and batch appears to be significant. In other words, this suggests that it's the type of popcorn and the batch size and their interaction which are what's important here. It doesn't look like the oil amount has any effect, so we can simplify this model down considerably. In fact, if we look at the four possibilities of small batches of gourmet, large batches of gourmet, small batches of normal, and large batches of normal, it turns out that it's specifically small batches of gourmet that perform better than the others. So that enables us to have a very good, simple explanation, which is presented here. This is a much simpler model. This just simply says, compare the small gourmet combination to everything else. So just to, let me just go back for a minute to show you. So in the original large model here, this has 7 degrees of freedom in our model. This is a relatively complex model. The overall R squared was 89% and the adjusted R squared was about 80%. Okay, so that's how good our complex model with all 7 terms was. We now have a model which only has 1 degree of freedom instead of 7, because it only has these 2 groups instead of having 8 groups. And you will see that the R squared has gone down quite a lot, but the adjusted R squared is almost the same. The adjusted R squared is still 79%. So this is, although it's a much simpler model with only 1 degree of freedom instead of 7, the adjusted R squared is almost the same. So this is a very nice simple explanation of a model where we started out with a relatively complex analysis of variance with our 2 by 2 by 2 combinations. So we had the 8 groups, and here we're being able to simplify it all the way down to 2 groups, indicating that nothing else really matters very much in terms of our outcome. Okay, so what about nested classifications? So nested classifications, if we had 2 nested classifications, we will generally have 3 sources of variability. Our first classification, our second nested classification 2 inside classification 1, plus the residual. So we would normally start out by checking whether the class differences within class 1 are important. In our example of schools and classes, that would mean checking whether classes within schools are different. Obviously, if they're not, then that means we can just really look at school differences. We wouldn't have to worry about differences between classes within schools. In fact, the nested situation may be more complex because our classification 2 may be a sample from classification 1. In this case, we would say the classification 2 is a random effect. So this alters our f-test. It means the error term needs to be more complicated and the correct statistical analysis is more complex because we need to adjust the denominator in our f-tests to account for the random effects part. So I will come back to this with an example in a few minutes. So what about our model choice objective? So in general, there's no limit to the number of classifications that we can consider in theory, although in practice it only works well if the sample size is much bigger than the total number of groups across all our classifications. So what we're trying to do is to find groupings such that individuals within the groups are similar while the groups themselves are different. So this helps us to understand what characteristics relate to our measured outcome variable. Again, remember, this does not prove causation, but it suggests a possible causation. In other words, that's why we use variability explained in a rather loose manner to make it clear that we don't imply causation, as there may be other alternative explanations, so that we can have several different groupings, each of which are useful, but where once we have used one of the groupings, the other groupings actually don't provide any further explanatory power. So just as in the regression models, we have three key assumptions. First of all, independent errors for different data points. Secondly, variability within groups is assumed to be the same. So this is just like across different x values for the regression models. And again, lastly, that for the test, the statistical test, we again have to assume that the errors follow a normal or bell-shaped distribution. In practice, analysis of variance is quite robust, but sometimes we can reduce divergence from these assumptions by transforming the data. So what can we do with transformations? Well, first of all, if we're doing just one-way analysis of variance, we can remove the assumption of equal variance using what's called Welch's analysis of variance. So this is coming back to our example with the drugs. So here we have actually 4 different tests of whether the variances are the same within our 3 groups. So you will see all 4 of these tests, none of them show a statistical difference in the variances across the 3 groups. But below we have got Welch's test, which is testing whether the means are equal, allowing that the standard deviations are not. So you'll see in Welch's test, the observed significance level is about 5.7%. This is somewhat bigger than the value we got where we were assuming the variances are equal. That's because Welch's test is less sensitive than the standard analysis of variance. But one could argue that given that the variances weren't significantly different, that in this case we don't need to take that extra step. Now, I said earlier on that we might have random effects in our analysis of variance. So there are 2 situations where we might have random effects. One was the example we mentioned before of students. That's a hierarchical effect. And we're going to look at a simple example of this below on animals. Another situation is where we have repeated measurements on the same individuals. So in both of those situations, we need to use analysis of variance methods that account for those random effects, which generally means that the denominator needs to change for the f-tests. So these methods can be labeled as random effects analysis of variance or as repeated measures analysis of variance. So we're first of all going to look at the animals example. Okay, so this is our animals example. This animals example is about trying to understand the distances that animals travel in different seasons. So we have 2 different animal species. That's our species variable, which is either fox or coyote. We have 3 animals for each species, subjects 1, 2, and 3, and we have 4 seasons of 1 year. So we have 24 data points, 2 species times 3 animals times 4 seasons. However, the animals within each species are clearly random samples within the species. So the species number is hierarchical within species. And then we also have 4 measurements for each individual. So we have repeated measurements for each individual. So we have both of these issues, repeated measurements for each animal and a hierarchy of animals within the species. So we need to modify the analysis of variance to take account of both of these. In JMP, this is very easy. First of all, we note that subject is nested within species, and that then we note that subject is a random effect, and we also include season as a factor. So then we get the output below, which shows that both species and season are both statistically significant. So let me scroll down a little bit. But the F-test has been modified to account for the fact that the species is tested relative to variation between subjects, whereas the season is tested relative to variation within subjects. So if you look at this down below, you will see it's got this extra word REML. I'm not going to go into the details of what REML is, but this just basically is telling us how it is divided up, the random components of this, and it's taking into account that there is a random effect for subject within species. Okay, so if you look on the right hand side, it's telling you the least square mean for each of these. So it's telling you here that coyotes travel about 5.9. I think this is miles. This is US data, whereas the foxes only travel about 3 miles. And if we look at it across the seasons, we can see that the animals travel furthest in the spring, second furthest in the summer, and they travel the least distance in the winter. Okay? And you'll see we've got the fixed effect test for species and season up there on the top right hand side, showing that these are both significant. Okay, so in this particular case, we're implicitly assuming we can ignore any interaction between species and season. I haven't included that in the model. Okay, so that brings us to the end of the analysis of variance section. Thank you.